Hi everyone, this is Joseph Paulraj. Today I'm going to talk about building high performance AI literature processing platforms. So AI has been a buzzword for past several years. And let's talk about how AI can be utilized with respect to the navigating through the complex ecosystem of the researchers out there. The research is happening every day. There are plenty of researches happening, and the publications out there are like thousands and thousands of publications. The challenge is not about publishing a research, it's about keeping it up. Without AI powered platforms, critical research discoveries, something which may be phenomenal or maybe utilized to build on top of, that's a vital component maybe for another research. So if you wanted to navigate through that and find out those things, it may be buried in the exponentially growing volume of publications. For an instance, 10,000 plus biomedical papers are published every day. So let's talk about RAG, Retrieval Augmented Generation, as a foundation pattern. Why do we need RAG? There are like lots of LLM power models, like we have Gemini, Claude Engine, Grok. There are lots of things out there. What is the value addition being done by the RAG? Let's talk about it through these slides. But the main idea is RAG prevents hallucinations. When you talk about the research discovery, we want accuracy. We want the correct details to be rendered. So RAG prevents hallucinations. It's about grounding LLM reasoning in authoritative references. Let's talk about the role of distributed vector database in there and its architecture. So unlike keywords, embeddings capture the context. Distributing indexes ensures sub-second retrieval at scale. So we are not only concerned about navigating through the complex ecosystem of researchers, we also want it to happen efficiently. So vector database helps with semantic understanding. We also have distributed indexing, so which means that its sharding across nodes enables parallel processing and fault. So now we are talking about the sub-second retrieval. Optimized nearest neighbor search algorithms maintain speed at scale. So we want to happen this entire research to be navigated through and get us the right truth of information in split second timing. That's what we care about. We care about the reliability, accuracy, and also the response time. Event driven microservice architecture. Elastic scaling during document search surges keeps ingestion and inference smooth. Benefits of this: independent scaling of components, fault isolation, a technology flexibility. And we can use messaging system like Kafka, stateless services, and event-driven workflows. So it's not about how we are going to implement it. We may use the mix and match of different tools and technologies, but we need to have an architecture which scales and helps us with respect to without being worried about the volume of the transactions. Efficient LLM inference pipelines. So here we are talking about the techniques like batching, reuse, and caching. They help us to cut cost drastically while enabling instant answer. Request batching means it's combining multiple requests to maximum GPU utilization. We have lots of GPU resource, but it's costly. We have to use it very wisely. We have to, if it is needed and if it is efficient, we need to combine multiple requests to maximize GPU utilization. Response caching, which means that storing common queries and responses to avoid the computations being done repeatedly, the same computations being done repeatedly. Model quantity, optimizing model size without sacrificing their quality. We talked about the RAG to bring more, avoid hallucination and to bring more accuracy in while navigating through the document search, getting the truth out of the research publications out there. It's not about getting the right information, with split second timing. It's also about keeping up with the research updates. Like researches change quickly. There are more and more research publications out there. Something might have changed. Something may be outdated and new information might be coming in. So we also need to keep up to date with the research out there. So real-time knowledge synchronization help with that. It's all about involving the techniques like continuous ingestions, incremental updates, conflict resolution, and knowledge integration. Entity extraction at scale. So we are going to implement domain-specific models to extract genes, proteins. Here I'm talking about the model specific to bioinformatics or biomedical. So domain-specific models extract genes, proteins, and diseases, merging them into knowledge graphs for deeper insights. Entity types like such as genes and proteins may have a relationship like causes and cost by. So those kind of entity types and relationship types are stored at scale. So which means we can navigate easily through these entities and their relationship and find out the right information which we need. And we also need to understand the horizontal scaling strategies. Rather than bigger machines, we scale horizontally, distributing embeddings and inferences across GPU pools. So we need to distribute, and horizontally scaling will help us to avoid cost when it's not needed and also help us to meet the demand when it's really needed. Caching layers and cost optimization. Caching ensures instant results without invoking a full pipeline, keeping latency low and cost sustainable. So we don't need to update everything every minute. If it is something frequently accessed query, and we don't need to update it every day, every hour or every 30 minutes or like that. We probably might update with the next incremental update. But until then, we can retrieve it from the cache to save some cost. So cache can be with the embeddings cache, retrieval cache, or response cache. Monitoring and observability. End-to-end monitoring captures throughput, latency, and inference quality. Observability ensures issues are caught before they escalate. So we have to capture performance metrics, throughput, latency, error rates, and resource utilization, quality metrics, anomaly detection, and distributed tracing to make sure that whatever we deploy, they work and meet the demand and help us to get the right information and right on time. Reliability and error handling. Failures are inevitable in any systems. So when we talk about the system design, we also need to talk about handling the failures. What matters is resilience. Graceful degradation ensures uninterrupted service. Resilience patterns means circuit breakers, retry with backoff, fallback request, redundant components. So graceful degradation may be simpler models as backup, cached responses when live fails, partial results when complete unavailable, clear error communication. So we need to adapt a technique which is suitable for that particular instance and make sure that it's not a complete failure while we work on to rectify that problem that is happening in the production. Infrastructure as code and CI/CD. This is a common technique used in the software engineering. So infrastructure as a code ensures reproducibility. CI/CD pipelines validate changes and rollouts updates safely. Infrastructure definition, like a Terraform, CloudFormation, Kubernetes manifest, automated testing. We can embed automated testings in the code file to make sure that's happening along with pipeline runs, CI/CD pipeline runs. Gradual rollout, canary deployments and blue-green strategies, performance fallback, continuous monitoring of the deployed changes, containerization and deployment strategies. So when we talk about the environment, the run environment of any code, we also need to talk about the containerization. So microservices run in isolated containers, orchestrated for scaling, resilience, and seamless update. So the benefits of container, it provides a consistent environment, isolated dependencies, efficient resource usage. Orchestration features, auto-scaling, self-healing, rolling updates, load balancing. So deployment strategies, when it comes to deployment strategies, we can adapt blue-green deployment, canary releases, feature flags, etc. So we also need to come up with the benchmarking and draw a line and do the performance validation. So benchmarks, they validate design goals. Testing under load failure scenarios guides capacity planning. So we have to define those matrices like latency. Like for an example, it should be less than 50 milliseconds for typical queries. Throughput, how many queries should be processed per second. Accuracy, how much accuracy we expect. We have to define those matrices and constantly monitoring that those matrices are met and we are on track and we deliver what we intended to deliver. And uptime, system availability, that's a very crucial part. Cross-domain applicability. Though I talked about biomedical research, the same patterns can be extended to law, finance, insurance, or any type of knowledge. For legal, for an instance, we can have case law, statutes, and regulatory documentation, documents. Finance, market reports, filings, and analysis. Technical documents, specifications, manuals, and standards. Historical archives like manuscripts, records, and cultural artifacts. In insurance industry, we may have plenty of documents. Conclusion. High performance platforms require carefully engineered pipelines. This blueprint accelerates discovery across science and industry. It's not about deploying in LLM for our need. It's about engineering an ecosystem around it. Then only we can achieve the accuracy, the speed, and also we keep up to date to avoid outdated information being transmitted to the critical science community. The architecture patterns we have explored provide foundation for building scalable, reliable, efficient AI literature processing platforms that can handle exponential growth of applications across domain. Thank you for this opportunity. I hope that this particular presentation would have helped few audiences, and thank you for this opportunity once again. Thank you.